You light a match, see a flame, feel heat, and you think you understand what's happening. Fire burns, releases heat, consumes fuel. Simple, except it's not. Not simple. Not even remotely what you think, because when you ask the most basic question, when you really ask why fire burns, when you try to understand what's actually happening at a fundamental level, you discover something absolutely terrifying about the nature of reality. You discover fire isn't a thing, isn't a substance, isn't an element like the ancients thought. Fire is a process. It's a chemical reaction happening rapidly. It's molecules being torn apart and reassembled. It's electrons jumping between energy levels. It's energy being released in the form of light and heat. And when you really understand this, when you see what's actually happening, you realize everything you thought you knew about fire was wrong, completely wrong, because fire doesn't burn, fire doesn't consume, fire doesn't destroy. Fire is just reorganization. It's atoms changing partners, it's energy changing forms. It's a reversible process governed by laws of thermodynamics. And the only reason it goes in one direction and not the other is probability, is entropy, is the second law. And that changes everything. Because it means burning isn't destruction, it's transformation. And transformation isn't an end, it's change. And change is reversible, in principle. And Richard Feynman understood this deeply. He had a way of looking at common processes, processes we all see but don't think about, and making you really see them, really understand them. And when he did this with fire, when he explained what actually happens when something burns, it was revelation, it was transformative. Because he didn't just tell you the chemistry, didn't just tell you that hydrocarbons react with oxygen to produce carbon dioxide and water. That's just description. He made you understand why. He made you see the energy, made you see bonds being broken and formed, made you see electrons reorganizing, made you see that fire is just the way the universe redistributes energy, how it finds the most probable configuration, how it maximizes entropy. And when you see it that way, when you understand fire not as destruction, but as reorganization, as energy transformation, you never look at a flame the same way again. Because it's not just fire burning, it's the universe doing what it always does, evolving toward the most probable state, spreading energy, increasing disorder, and fire is just a dramatic, visible manifestation of that fundamental process. It's entropy in action, it's the second law made visible, it's destruction that isn't destruction, it's transformation. And transformation is everything, because everything that happens, everything that changes, everything that evolves is transformation. And fire is just an example you can see, an example you can feel, an example that captures attention because it's bright and hot and dangerous. But fundamentally, it's just chemistry, just reorganization of atoms, just change of energy from one form to another. And that's what everything is, always. Before we go deeper, don't forget to subscribe to the channel and leave a like on the video. Now, let's get back to it. Let me tell you what actually happens when something burns. Not the simplified version, not the textbook version, the real version, the version that actually explains what's happening at the atomic level. You have combustible material, wood, paper, gasoline, whatever. And that material is made of molecules, large, complex molecules, hydrocarbons mostly. Carbon and hydrogen bonded together in chains and rings, and those molecules are stable. They have energy, energy stored in the bonds between atoms, and the energy is high, higher than it would need to be if the atoms were in a different configuration. But they don't change, not spontaneously, because there's a barrier, an energy barrier, activation energy. You have to supply energy to break bonds before new bonds can form, have to push the system over the barrier, and then, once over the barrier, the system can roll down to a lower energy state, can form new molecules, more stable molecules, with less energy. And the difference in energy, the energy released, comes out as heat and light, as fire. And that heat, that released energy, provides activation energy for nearby molecules, breaks their bonds, pushes them over the barrier, and they burn and release more energy, which breaks more bonds. And you have a chain reaction, self-sustaining, propagating. That's fire. That's combustion. It's a chain reaction where energy released from one molecule burning provides activation energy for the next. And what's actually happening at the atomic level? Hydrocarbon molecules colliding with oxygen molecules. And when they collide with enough energy, Bonds break. Carbon-hydrogen bond breaks. Carbon-carbon bond breaks. Oxygen-oxygen bond breaks. And atoms reorganize. Carbon binds to oxygen. Hydrogen binds to oxygen. And new molecules form. Carbon dioxide, water. And those new molecules have less energy than the old molecules. Their bonds are stronger, more stable. And the difference in energy, energy that was stored in old bonds but isn't needed in new bonds, is released as heat, as light, as motion of molecules, as kinetic energy. And that energy is what you feel, is what you see, is fire. But fundamentally, fire isn't a thing, isn't a substance being released. It's energy being released. It's transformation of chemical energy into thermal energy and light. And that transformation is irreversible. Not because it can't be reversed in principle, but because it's statistically unlikely. Because energy spread as heat in billions of molecules moving randomly won't spontaneously recollect and reform chemical bonds. It could, in principle. Laws of physics don't forbid it. But it's so unlikely it will never happen. Not in the lifetime of the universe. Not in 1,000 lifetimes. It's possible, but not probable. And the difference between possible and probable is everything. It's the second law of thermodynamics. It's entropy. It's the arrow of time. It's why fire burns in one direction and not the other. Not because it can't, but because it won't. Because probability says it won't. And probability, at the scale of billions of molecules, is certainty, is law. And this is disturbing because it means fire, something so dramatic, so powerful, so transformative, is just statistics, is just probability, is just billions of molecules doing what's most likely. And what's most likely? Spreading energy, increasing disorder, maximizing entropy. And that's all fire does. All fire, all combustion, all chemical reactions. It's the system finding the most probable state and doing it through reorganization of atoms, through breaking and forming bonds, through release of energy. And you see that release of energy as flame, as heat, as light. But fundamentally, it's not fire burning, it's entropy increasing. It's the universe evolving toward the most probable state, and fire is just the way this happens. Just the visible manifestation of a fundamental process. And once you see this, once you understand fire as entropy, as probability, as statistical evolution toward the most probable state, you never think about fire the same way again. Because it's not magic, not a mystical element, not a force of destruction. It's just chemistry, just thermodynamics, just atoms doing what atoms do, reorganizing, releasing energy, increasing entropy. And that's all. That's fire, and that's everything. Always was, always will be, and now you know. And you can't unknow it, and this should break your mind, because it means everything you thought you knew about fire was wrong. And if you were wrong about fire, what else are you wrong about? Everything? Maybe, probably, because reality isn't what it seems, never is. And the more you look, the more you understand, the stranger it gets, always. And fire is just the beginning. Now, let's talk about energy, because that's what fire really is. It's release of energy. And you need to understand where that energy comes from and where it goes. Because when you light a match, when you burn wood, when you explode gasoline, energy doesn't appear from nowhere. It doesn't disappear into nothing. It's conserved, always. Law of conservation of energy is absolute, unbreakable. So the energy in the flame, the heat you feel, the light you see, all comes from somewhere and goes somewhere. And understanding those places, understanding the flow of energy, is understanding what fire really is. So where does the energy come from? Comes from chemical bonds. Comes from energy stored in the arrangement of atoms and fuel molecules. And that arrangement has energy because electrons and atoms are in a specific configuration. A configuration that's not the lowest possible energy, but it's stable. It's a local minimum. It's a valley in the energy landscape. And to get out of that valley, to change to a different configuration, you have to supply energy, have to push over the hill, activation energy. And once over the hill, the system can roll down to a deeper valley, to a lower energy configuration. And the difference in energy between the original valley and the new valley is released as heat, as light, as kinetic energy of product molecules. And that released energy is what we call heat of combustion. It's a specific amount of energy per amount of fuel. And it's measurable, it's predictable, it's a property of specific molecules. And here's the fascinating part. The energy stored in fuel, in wood or gasoline or coal, isn't new, wasn't created recently. It comes from sunlight, from photosynthesis. Plants take sunlight, energy from photons, and use it to build molecules, to take carbon dioxide and water and reorganize them into sugars, into hydrocarbons. And that process requires energy, a lot of energy, energy that comes from sunlight. And that energy is stored in the bonds of the molecules the plant builds. And when you burn wood, when you burn paper, when you burn anything that came from a plant, you're releasing that energy, energy that was captured from sunlight millions of years ago, stored in chemical bonds, and now released, transformed back into heat and light. It's a cycle. It's a flow of energy from the sun to plants to fuel back to heat and light. And fire is just part of that cycle. It's the release. It's the transformation of stored energy back into dispersed forms, back into heat, back into light, back into random motion of molecules. And that's what entropy is. It's the spreading of energy. It's transformation of concentrated, organized, useful energy into dispersed, disorganized, useless energy. And fire does that. Dramatically, visibly, rapidly. But fundamentally, it's just what everything does. Everything that happens increases entropy. Everything spreads energy. Everything evolves from concentrated to dispersed, from organized to disorganized, from useful to useless. And fire is just an example, just a visible manifestation of a universal process. And once you see this, once you understand fire as part of a larger energy cycle, as a manifestation of the second law, you realize fire isn't special. It's just chemistry, just thermodynamics, just what happens when a system evolves from higher energy state to lower energy state, and releases the difference. Now, let me be very specific about what's happening at the molecular level, because details matter. Details are where understanding lives. You have a hydrocarbon molecule, let's say methane, CH4, carbon bonded to 4 hydrogens, and you have oxygen, O2, 2 oxygen atoms bonded together. And when methane and oxygen collide with sufficient energy, bonds break. CH bond breaks. O bond breaks. And atoms reorganize. Carbon binds to 2 oxygens forming CO2. Hydrogens bind to oxygens forming H2O. And that reorganization releases energy. Why? Because bonds in CO2 and H2O are stronger than bonds in CH4 and O2. Stronger bond means lower energy, means more stable. And the difference in energy is released. Specifically, for methane, the reaction releases about 890 kilojoules per mole. It's a specific number, it's measurable, it's predictable, and it comes from the difference in bond strengths, from the difference in how much energy is needed to hold atoms together in different configurations. And that energy, those 890 kilojoules, doesn't disappear, goes into the product molecules as kinetic energy, as motion, and those molecules collide with other molecules, transfer energy, spread it, and you feel that as heat, and see it as light when some molecules get excited enough to emit photons, and that's the flame, that's fire. It's energy being spread, being transformed from chemical energy into thermal energy and light. And the process is irreversible, not because it can't be reversed, but because reversal would require collecting all that dispersed energy, all that thermal energy spread across billions of molecules, and concentrating it back into chemical bonds. And that won't happen, not spontaneously, because it's statistically unlikely. It's possible, but unlikely. And the difference is everything. And there's another layer, a deeper layer. Because when you ask why some bonds are stronger than others, why CO2 has lower energy than CH4 and O2, you're really asking about quantum mechanics, about how electrons organize around atoms, and the answer involves orbitals, energy levels, Pauli exclusion principle, exchange energy, all the quantum physics of how electrons behave when atoms come close. And when you calculate that, when you solve the Schrödinger equation for molecules, you get bond energies. You get how much energy is needed to hold atoms together. And those numbers match experiments perfectly. And that tells you we understand, deeply, not just descriptively, but fundamentally, we know why bonds have the strengths they have. Know why some molecules are more stable than others. Know why reactions release the specific energy they release. It all comes from quantum mechanics, from how electrons behave, from the structure of atoms and molecules at the most fundamental level. And fire, that dramatic and visible process, is just a manifestation of those fundamental quantum laws. It's electrons reorganizing, its orbitals changing, its energy being released as the system finds lower energy configuration. And we see that as flame, but fundamentally it's just physics, just quantum mechanics, just the laws that govern how particles behave. And those laws are known, are tested, are precise, and explain everything, including fire, including why it burns, including how much energy it releases, including everything. And this brings us to a profound insight, an insight Feynman loved to emphasize, that everything is energy, matter is energy. E zerm besh MC2. Chemical bonds are energy, heat is energy, light is energy, motion is energy. Everything is energy in different forms, and what we call processes, what we call changes, are just transformations of energy from one form to another. And fire is transformation. It's chemical energy becoming thermal energy and light, and that transformation is governed by laws. Conservation of energy. Second law of thermodynamics. Laws that are never violated, never. And those laws explain everything about fire. Explain why it burns. Explain how much heat it releases. Explain why it's irreversible. Explain everything. And once you understand those laws, once you see fire through that lens, you realize fire isn't mystery, isn't magic, it's just physics, just thermodynamics, just conservation of energy and increase of entropy. And that should be satisfying, should be final. But it's not, because there's still a question, a deeper question. Why those laws? Why is energy conserved? Why does entropy increase? And we don't have an answer, not a final one. We just know it's how it is, that the universe works this way. And fire is consequence, is manifestation, is example, and that's all we need to know, for now, until we discover deeper, if there is deeper, and maybe there is, or maybe there isn't. But for now, we have energy, we have entropy, we have laws, and we have fire, and fire makes sense, completely, once you understand. And now you understand, and you can't unknow it, and that's a gift of physics, a gift of understanding, and you'll never look at a flame the same way again. Now, let's talk about the flame itself, because when you look at fire, what do you actually see? You see light, you see colors, yellow, orange, sometimes blue, and you think you're seeing fire, but you're not. You're seeing radiation. You're seeing photons being emitted by excited molecules and atoms. And those photons have specific energies, specific wavelengths, specific colors. And those colors tell you something deep about what's happening, about temperature, about which molecules are present, about how complete the combustion is. Colors aren't accidental, they're signatures, they're evidence. They're the way fire tells you what it's doing. And if you know how to read it, if you understand what colors mean, you can look at a flame and know exactly what's happening at the molecular level. Let me show you how. When a molecule burns, when chemical reaction releases energy, that energy doesn't come out uniformly, doesn't disperse instantly. First it goes into the product molecules, CO2, H2O, other molecules. And those molecules become excited, have extra energy, energy in the form of vibration, rotation, electronic motion. And those excited molecules don't stay excited. They relax, release energy, and one way they release energy is by emitting photons, light. And the energy of those photons, the wavelength, the color, depends on how much energy the molecule had, how excited it was. And that depends on temperature, on how hot the flame is. So flame colors tell you temperature. Red flame is relatively cool, about 1,000 to 1,200 Kelvin. Yellow-orange flame is hotter, 1,300 to 1,600 Kelvin. Blue flame is even hotter, 1,800 to 2,000 Kelvin or more. And those temperatures aren't arbitrary. They're determined by how much energy is being released, by how fast the reaction is, by how much fuel is available, by how much oxygen is present. Everything affects temperature, and temperature determines color through black body radiation, Planck's law, same laws that describe why stars have the colors they have, why the sun is yellow, why hot stars are blue, Why cool stars are red. Same laws, same physics. Fire is just a small star, a small region where matter is hot enough to emit visible light, and the color tells you how hot, and how hot tells you how much energy is being released. And how much energy is being released tells you how efficient the combustion is, how much energy is coming out of the available fuel. And that's useful. It's practical. It's how engineers design furnaces, engines, rockets. They look at the flame, analyze the color, measure the temperature, and adjust fuel, oxygen, flow, everything to get the combustion they want, to extract the energy they need, to maximize efficiency. And it all comes from understanding what colors mean, what the flame is telling you. And once you understand the physics behind the colors, you can look at any fire and read it, can see the temperature, can see the efficiency, can see if it's burning clean or producing soot, all from the colors, all from the light. But there's more, because colors don't just come from blackbody radiation. They also come from specific emissions, from specific atoms and molecules. Sodium, for example. If you have sodium in a flame, it emits very specific yellow light, very specific wavelength, 589 nanometers. Sodium D lines, and you can see that clearly if you look through a spectroscope. And even without a spectroscope, you can see it. Table salt in a flame produces characteristic bright yellow, and that yellow isn't from temperature, it's from sodium, from electrons in sodium atoms being excited and then relaxing, and emitting photons of specific energy. And that energy corresponds to yellow, and you see it, and that's spectroscopy. It's how chemists identify elements. They burn a sample, look at the colors, analyze the wavelengths, and identify which elements are present. It's a powerful tool. It's precise. And it works because each element has unique signature, unique set of energy levels. And when electrons jump between those levels, they emit photons of specific energies, specific colors. And those colors are like fingerprints. They're unique. They're identifiable. And you can see them in a flame if you know where to look, if you know what to look for. And this transforms flame from something decorative into something informative, from something beautiful into something useful, from something you just look at into something you read. That tells you secrets about what's burning, about which atoms are present, about what's happening at the most fundamental level. And then there's soot, because not all combustion is complete. Not all carbon oxidizes completely to CO2. Sometimes you get partially oxidized carbon, carbon monoxide, or unoxidized carbon, solid carbon particles, soot. And that soot gets hot, becomes incandescent, and emits light. Not light of specific wavelength, but blackbody radiation, broad spectrum. And that incandescent soot is what gives most flames their yellow-orange color. It's not the temperature of the gas, it's the temperature of solid carbon particles floating in the flame. And when you see a yellow flame, you're seeing soot. You're seeing incomplete combustion. You're seeing carbon that didn't oxidize completely. And that tells you something. Tells you there's not enough oxygen, or that the fuel isn't mixed properly, or that the temperature isn't high enough. And if you want efficient combustion, if you want to extract maximum energy, you need to eliminate soot, need to provide more oxygen, need to mix better, need to burn hotter. And then you get blue flame, clean flame, flame where all the carbon is oxidizing completely to CO2, where all the energy is being extracted, where combustion is efficient. And you can see that, can see the difference. Yellow flame versus blue flame, sooty versus clean, inefficient versus efficient, all from the colors, all from the light. And once you know what you're looking at, once you understand the physics, you can optimize, can adjust, can control fire, can make it do what you want. And that's power, power that comes from understanding, from knowing what's actually happening, and not just accepting fire as mystery, as magic, as something that just is, but understanding it deeply, fundamentally, and using that understanding. And let me give you a specific example. Candle flame. You look at it, see yellow, see orange, maybe some blue at the base, and each color tells you something. Blue at the base is where combustion is most complete, where vaporized wax is mixing with oxygen and burning efficiently. Temperature is high, about 1400 Kelvin, and combustion is producing mainly CO2 and H2O. But as the gases move upward, as they get further from the source of fresh oxygen, combustion becomes less complete, temperature drops, and Carbon doesn't oxidize completely, forms soot, and that soot becomes incandescent and emits yellow-orange light, and you see that. You see the yellow zone in the middle of the flame, and that yellow zone is soot, is partially burned carbon, is inefficient, and at the top of the flame, the soot cools, stops glowing, and you see black smoke, unburned carbon escaping, wasted, and all of this you can see. All of this you can read from the colors, from the structure of the flame, and once you understand, once you see what's actually happening, a candle isn't just beautiful anymore. It's informative. It's a demonstration of thermodynamics, of combustion, of energy flow, of how temperature and oxygen availability affect burning efficiency. And it's all there, visible, measurable, understandable, if you know how to look, and now you know. And you'll never look at a flame the same way again, because it's not just pretty, it's physics, it's chemistry, it's thermodynamics happening in real time, and you can see it, can read it, can understand it. And that's extraordinary. That's the power of knowledge, power of understanding, and it transforms something common into something profound, something everyday into something wonderful. Just because you know, just because you understand, and you can't unknow it, and you wouldn't want to, because knowledge is a gift, and you just received it. Now let's talk about the most disturbing aspect of fire, the aspect that really breaks your mind once you understand it. Because when you burn wood, when you burn paper, when you burn anything, where does it go? You see ashes, small amount of residue, and you think the rest disappeared, was destroyed, consumed by fire. But it wasn't, couldn't have been. Law of conservation of mass is absolute. Matter doesn't disappear, isn't destroyed, just changes form. So, where did it go? And the answer is disturbing. It went into the air, literally. The carbon in the wood, the carbon you see as solid, visible structure, combined with oxygen to form CO2, carbon dioxide, gas, invisible, and it floated away. And the hydrogen in the wood, combined with oxygen to form H2O, water, vapor, also invisible, and also floated away. And that's where the mass went, not destroyed, transformed, from solid to gas, from visible to invisible. And it floated away, and you don't see it, don't track it, don't think about it, but it's there. Every atom, every carbon, every hydrogen, every oxygen still exists, just in different form, in different molecules, dispersed in the atmosphere. And that's disturbing, because it means burning isn't destruction, it's dispersion. It's transformation of concentrated into dispersed, of organized into disorganized, of visible into invisible, and you lose track, lose control. But the atoms are still there, always, forever, can't be destroyed, only reorganized. And that's true for everything. Everything you burn, everything you destroy. Atoms persist, always, and that's law. Law of conservation of mass, law of conservation of energy, laws that are never violated. And here's what's really disturbing. If you could track the atoms, if you could follow them, you'd see they don't go far. CO2 molecules rise, disperse in atmosphere, but eventually, through photosynthesis, through plants, they're captured again. Carbon is incorporated into new wood, new plant, new living tissue, and the cycle continues. And those same carbon atoms, atoms that were in the tree you burned, will eventually be in another tree, or in you. Because you eat plants, or eat animals that eat plants, and those carbon atoms become part of you. And then when you die, when you decompose or are cremated, those atoms are released again, back into atmosphere, back into the cycle, and the cycle continues, forever. The carbon atoms in your body right now as you're reading this, have been in countless other organisms, have been part of dinosaurs, of ancient trees, of bacteria, of everything, and will be again. Because atoms don't die, aren't destroyed, just circulate through the biosphere, through atmosphere, through oceans, through rocks, through everything. And you're just a temporary configuration, just a temporary arrangement of atoms that existed before you and will exist after. And fire is just one of the processes that redistributes those atoms, that breaks arrangements and allows new ones. And from that perspective, fire isn't destruction. It's liberation. It's return of atoms to the pool, to the cycle, to the continuous process of reorganization. And you're part of that process, always have been, always will be, and fire just makes that visible, makes it dramatic, makes it obvious. But it's always true, always happening, just slower, usually, more subtly, but always. Always reorganization, always cycle, always transformation, never destruction. Because destruction doesn't exist, only change, and change is everything. And let me be very specific about numbers. Because when you burn 1 kilogram of wood, you don't get 1 kilogram of ash. You get maybe 10 grams, maybe 20, small fraction. So where did the other 980 grams go? They went into the air as CO2 and H2O. And you can calculate exactly how much. Wood is roughly 50% carbon. So 1 kilogram of wood contains 500 grams of carbon. And each carbon atom, when it burns, combines with 2 oxygen atoms to form CO2. And CO2 has mass of 44 grams per mole, and carbon has mass of 12 grams per mole. So each gram of carbon produces 44 divided by 12 grams of CO2, about 3.7 grams. So 500 grams of carbon produce 1,850 grams of CO2, almost 2 kilograms, of gas, invisible, and that goes out, floats away. And you don't see it, but it's there. And hydrogen, roughly 6% of wood, 60 grams, combines with oxygen to form water, and produces 540 grams of H2O, vapor, also invisible, also floating away. So you started with 1 kilogram of wood, added 2 kilograms of oxygen from the air, and ended up with 1,850 grams of CO2, 540 grams of H2O, and maybe 20 grams of ash. Total, 2,410 grams. And that matches, exactly. 1 kilogram of wood plus 2 kilograms of oxygen, 3 kilograms total, minus 20 grams that remain, as ash, gives 2,980 grams that went out as gas. And the numbers match, perfectly, because mass is conserved, always. And if you track every atom, if you account for everything, you'll see. Nothing was destroyed, everything was transformed, and that transformation is predictable, is calculable, is law. And this brings us to a profound insight, an insight that changes how you think about destruction, because destruction, in the common sense, doesn't exist. You can't destroy matter, can't make it disappear. You can only reorganize it, and fire is reorganization. It's transformation of organized solid into dispersed gases, and those gases are as real as the solid was, have the same mass, same atoms, just different arrangement. And from that perspective, burning a book doesn't destroy the information in the physical sense, destroys the organization, destroys the specific arrangement of molecules that encoded the information. But the atoms still exist, and in principle, if you could track every atom, if you could measure exactly where each one went, you could reconstruct, could reverse the process, could reassemble the book, molecule by molecule, atom by atom, and you'd have the book back with the same information. It's possible, in principle. Laws of physics don't forbid it, but it's impossible in practice. Why? Because the atoms dispersed, mixed with trillions of other molecules in the atmosphere. And tracking them, collecting them, reassembling them, would require knowledge of position and velocity of every molecule. And that violates uncertainty principle. And even if it didn't, it would require absurd amount of information. More information than could be stored in any physical system. So it's impossible, practically, but not in principle. And that distinction matters, because it tells you destruction isn't fundamental, isn't written into the laws of physics. What's written is conservation, conservation of energy, conservation of mass, conservation of information at quantum level. And those laws say nothing is really destroyed, just transformed, just reorganized, just dispersed. And dispersion is what makes reversal impossible practically, but not in principle. And that's profound. That's disturbing. That changes how you think about destruction, about ending, about death. Because everything is transformation. Everything is reorganization. And atoms persist. Always. And Feynman loved this point. Loved emphasizing that conservation isn't just a convenient law. It's deep. It's fundamental. It's what makes physics possible. Because if energy weren't conserved, if mass weren't conserved, you couldn't make predictions, couldn't calculate, couldn't know what will happen. But because they are conserved, because there are quantities that never change, you can track, can calculate, can predict. and that's power. Power of understanding, power of control. And when you apply that to fire, when you see fire as mass-conserving, energy-conserving reorganization, you see it's not mystery, not magic. It's predictable, it's calculable, it's understandable, and you can use it, can control it, can make it do what you want, extract specific energy, produce specific products, achieve specific temperature, all because you understand conservation, because you understand atoms don't disappear, just reorganize. And if you control the reorganization, if you control the conditions, you control the outcome. And that's engineering, that's technology, that's application of understanding. And it all comes from seeing fire not as destruction, but as transformation, as reorganization, as process governed by laws we know, laws we've tested, laws that work. And once you see it that way, once you understand fire as physics, as chemistry, as predictable and controllable process, you never think about it the same way again. Because it's not a force of destruction. It's a tool, it's a process, it's a transformation you can use, that you can control, that you can understand. And understanding is power. Always has been, always will be. And now you have that power, that understanding, and you can't lose it. And you wouldn't want to, because it's precious, it's transformative, it's a gift of physics, of science, of Feynman, and now it's yours, forever. Now, let's talk about control, because once you understand what fire really is, once you see it as a chemical process governed by laws, you realize you can control it, can make it do what you want. And humanity has been doing this for thousands of years, but most people don't understand what they're doing. They just know it works, that if you do certain things, you get certain results. But when you understand the physics, when you understand the chemistry, you can do much more, can optimize, can innovate, can create completely new types of combustion, completely new types of fire, because you understand the variables, understand what controls the process. And those variables are simple: fuel, oxygen, temperature. Those three things determine everything about fire: how fast it is, how hot it is, how much energy it releases, what products it forms, everything. And if you control those three variables, you control fire completely. So let me show you how. First, fuel. Different fuels release different amounts of energy. Hydrogen, for example, releases more energy per gram than any other chemical fuel, about 142 megajoules per kilogram. That's enormous, much more than gasoline, about 46 megajoules per kilogram, or wood, about 16 megajoules per kilogram. So if you want maximum energy per mass, you use hydrogen. That's why rockets use hydrogen. Maximum energy, maximum thrust. But hydrogen has problems. It's a gas, hard to store, hard to handle, dangerous, explodes easily. So for most applications, you use something else. Gasoline, kerosene, methane, depends on what you need, depends on what constraints you have, depends on trade-offs. Second, oxygen. Combustion requires oxygen. And the more oxygen you provide, the faster it burns, the hotter it gets, the more energy it releases per time. Air is about 21% oxygen, rest is mostly nitrogen, and that nitrogen dilutes combustion, absorbs heat, reduces temperature. So if you want hotter, faster combustion, you use pure oxygen, or enriched air, more oxygen, less nitrogen. And that's what's done in industrial furnaces, in welding torches, in rockets. You provide pure or nearly pure oxygen, and you get much higher temperature, much more energy, much more rapidly. But again, there are trade-offs. Pure oxygen is dangerous. Things that wouldn't burn normally burn in pure oxygen, violently, so you have to be careful, have to control, have to understand the risks. And then there's ratio of fuel to oxygen. And there's an optimal ratio, stoichiometric ratio, where you have exactly enough oxygen to burn all the fuel, not too much, not too little, exactly right. And at that ratio, you get maximum temperature, maximum efficiency, maximum energy. Too much fuel, and you get incomplete combustion, soot, waste. Too much oxygen, and you dilute the flame, temperature drops, efficiency drops. So you have to balance, have to control the ratio, and if you do it correctly, if you get the ratio right, you get perfect combustion, clean, efficient, maximum. And you can see that. can see it in the flame color. Blue means right, yellow means too much fuel, and you adjust, and optimize, and control. Third, temperature. Combustion requires minimum temperature. Activation energy. You have to supply enough energy to break bonds, to start the reaction. And once started, the reaction releases energy, and that energy keeps the reaction going, keeps the temperature high, and the cycle continues. But to start, you need a spark, need a flame, need something to provide initial activation energy. And the higher the initial temperature, the easier to start. And once started, the higher the temperature, the faster the reaction goes, the more energy it releases, and temperature rises, and reaction accelerates, and you get a feedback loop, self-reinforcing, and that can lead to explosion. If temperature rises fast enough, if reaction accelerates fast enough, you get very rapid release of energy, very rapid expansion of gases, and that's explosion. And you can control that. Can control it by controlling temperature, by controlling how fast energy is released, by controlling conditions. And if you do it correctly, you get controlled release. Engine, turbine, power generator. But if you lose control, if temperature rises too fast, you get explosion. And that can be useful for mining, for demolition, for propulsion. But it has to be controlled, has to be understood, has to be done carefully. And it all comes from understanding temperature, from understanding activation energy, from understanding how temperature affects reaction rate. And once you understand, you can control, can make fire do what you want, burn slow and steady, or fast and explosive. It all depends on you controlling the variables, controlling the conditions, controlling the process. And let me give you specific examples. Candle, slow, steady combustion. Why? Because fuel is supplied slowly. Wax melts, vaporizes in the wick, and burns. But the rate is controlled by how fast heat melts the wax, how fast wax rises up the wick. And that's a self-regulating process. If the flame gets too big, too hot, it melts more wax, but also burns faster, and uses wax faster than it can be supplied, so the flame shrinks, and temperature drops, and less wax melts, and flame gets smaller, and reaches equilibrium, self-regulating, self-balancing, and burns steadily for hours. Car engine, fast controlled combustion, explosions, thousands per minute. Why? Because fuel and air are mixed, compressed, heated, and then ignited by spark, and burn very fast, explosively, and push piston, and transfer energy, and cycle repeats, thousands of times per minute. And you get power, motion, useful energy, but controlled, timed, regulated, by valves, by ignition, by control system. And it all works because you understand combustion, understand what controls rate, what controls temperature, what controls energy, rocket, most extreme combustion, hottest, fastest, most energetic. Why? Because you supply fuel and pure oxygen in perfect ratio, and it burns immediately, violently, and releases enormous energy, and creates enormous thrust, and propels rocket, but controlled, regulated, by pumps, by valves, by sophisticated control systems, because it has to be controlled, has to be precise, or it fails, or explodes, or goes off course. And it all depends on understanding combustion, on understanding the variables, on controlling them perfectly, precisely, always. And finally, let me talk to you about efficiency, because not all energy and fuel is extracted. Not all energy becomes useful work. Much is wasted, as heat, as hot gases escaping, as incomplete combustion. And efficiency is about minimizing waste, about maximizing useful energy you extract. And efficiency depends on design, on control, on optimization. Car engine, for example, is maybe 25 to 30% efficient. That means only 25 to 30% of energy in gasoline becomes motion. Rest is wasted as heat, in exhaust gases, in engine cooling. And you can improve that. Can improve efficiency by improving combustion, by improving fuel and air mixing, by improving ignition timing, by improving compression. And each improvement increases efficiency, extracts more energy, wastes less. And that's what engineers do, what technology does. optimizes, improves, extracts more from same resources. And it all comes from understanding physics, from understanding thermodynamics, from understanding what limits efficiency, what causes waste, and how to minimize it. And when you understand, when you see fire as optimizable process, you realize there's no fundamental limit, no maximum efficiency beyond which you can't go. There are only practical limits, limits of materials, limits of design, limits of technology, but those limits can be pushed, can be exceeded, can be improved, and that's what we do, constantly. Improving engines, improving furnaces, improving rockets, improving everything that uses fire, everything that uses combustion, and all because we understand, because we know what fire is, how it works, how to control it, and how to optimize it. And that knowledge is power, is capability, is what allows us to use fire not just as destructive tool, but as constructive tool, as energy source, as engine of civilization. And it all comes from understanding, from seeing fire not as mystery, but as physics, as chemistry, as process, and processes can be controlled, can be optimized, can be used. And that's what we do. And now you understand how and why. And you'll never see fire the same way again, because it's not just flame, it's technology, it's science, it's applied understanding, and it's extraordinary. And this brings us back to the beginning. Why does fire burn? And now you know. It doesn't burn, not in the way you thought. There's no destruction, no consumption, no ending. There's just transformation, reorganization of atoms, breaking of bonds, formation of new bonds, release of energy, spreading of energy, increase of entropy. That's fire, that's combustion, that's what's actually happening. And once you see it that way, once you understand fire as physics, as chemistry, as thermodynamics, you never think about it the same way again, because it's not magical, not mystical, not a force of destruction. It's a process, it's transformation, it's reorganization governed by laws we know, laws we've tested, laws that work, always, without exception. And those laws are beautiful, are elegant, are profound. Conservation of energy, conservation of mass, increase of entropy. Fundamental laws that govern not just fire, but everything. Every process, every change, every transformation, and fire is just an example, a dramatic example, a visible example, an example that captures attention. But fundamentally, it's just chemistry, just physics, just atoms doing what atoms do, reorganizing, releasing energy, increasing entropy, and that's all. And it's enough, because when you understand that, when you really grasp that, you see fire isn't special, it's universal. It's a manifestation of laws that operate everywhere, always, and that's profound, that's transformative. That changes how you see the world, because everything is transformation, everything is reorganization, everything is process, and nothing is destroyed, never, just transformed, always. And Feynman understood this, deeply, and loved communicating it, loved making people see, really see, what was happening, not just superficially, but deeply, fundamentally. And when he talked about fire, when he explained combustion, it wasn't just a chemistry lesson, it was revelation. It was invitation to see the world differently, to see processes instead of things, to see transformation instead of destruction, to see continuity instead of ending. And that shift in perspective is precious, is liberating, is mind expanding, because it frees you from fear of destruction, from fear of ending, from fear of loss. Because if nothing is destroyed, if everything is just transformed, then there's no real ending, no real loss. There's just change. And change is all there is. Always was, always will be. And you're part of that. You are transformation. You are process. You are temporary reorganization of atoms that existed before you and will exist after. And fire is just the way some of those atoms reorganize. Rapidly, dramatically, visibly, but not fundamentally different from any other transformation, from any other change, from any other process. It's all reorganization. It's all transformation. It's all governed by the same laws. And those laws are knowable, are understandable, are testable. And when you know them, when you understand them, when you use them, You have power. Power to control, power to predict, power to create. And that power comes from understanding, from seeing through appearances, from seeing deep structure, from seeing the laws that govern, and using those laws. And that's science. That's physics. That's the gift Feynman gave us, and now it's yours, forever. And let me give you a final thought. A thought Feynman loved. A thought about beauty. Because when you understand fire, when you see how it really works, you might think the beauty disappears, that the magic disappears, that the mystery disappears, and all that's left is mechanics, dry, unpoetic. But the opposite is true. Beauty increases because you see more. You see layers, you see depth, you see connections. When you look at a flame, you don't just see yellow and orange. You see black body radiation. You see incandescent soot. You see emissions from excited atoms. You see temperature. You see reaction rate. You see efficiency. You see everything. And each layer adds beauty, doesn't subtract, because each layer is real, is true, is part of what's happening. And the more you know, the more you see. The more you appreciate, the more you marvel, because reality is richer than appearances, always. And science doesn't remove beauty. It adds, it multiplies, it transforms superficial beauty into deep beauty. And that deep beauty is more satisfying, more lasting, more real, because it's based on understanding, on knowledge, on truth. And truth is always more beautiful than illusion, always more satisfying, always more valuable. And when you see fire through the lens of science, through Feynman's understanding, you see not less beauty, but more, infinitely more, because you see what's really there, and what's there is extraordinary. And now, when you light a match, when you see a flame, when you feel heat, you know, it's not mystery, not magic. It's atoms reorganizing, it's bonds, breaking and forming, it's electrons jumping between energy levels. It's energy being released as light and heat. It's entropy increasing. It's the second law in action. It's visible thermodynamics. It's chemistry happening. It's physics in real time. And you can see it, can understand it, can appreciate it, not just as something beautiful, but as something profound, as manifestation of fundamental laws, as window into the structure of reality. And that window is a gift. Gift of science, gift of Feynman, gift of understanding. And it can't be taken away, can't be unknown. It's in you, forever. And it changes how you see the world. Because now when you see fire, you see more. You see truth. And truth is beautiful. More beautiful than any illusion. Deeper than any mystery. More satisfying than any magic. Because it's real, it's true, it's understandable, and it's yours. Forever. And nobody can take that away. Nobody can make you unknow. Because once you understand, once you see, you can't unsee. And that's power. Power of knowledge, power of understanding, power of truth. And that power transforms you, transforms how you think, how you see, how you experience the world, and makes everything richer, deeper, more wonderful, because you see what's really there. And what's there is extraordinary, always was, always will be. And now, you know, and you can't unknow, and you wouldn't want to, because knowledge is a gift, and you just received it, and it's yours. Forever. And finally, let me tell you why this matters. Why understanding fire matters. Not just because it's interesting, not just because it's beautiful, but because it's fundamental. Because fire is how civilization works. How we get energy, how we cook food, how we heat homes, how we move vehicles, how we generate electricity, how we manufacture everything. Everything depends on combustion, on fire, on transformation of chemical energy into other forms. And the better we understand, the more efficiently we use it. The more energy we extract, the less we waste, the more we can do. And that matters. Matters a lot. Because energy is everything. It's what enables civilization, what enables technology, what enables progress. And understanding fire is understanding energy, is understanding transformation, is understanding how to use resources, how to optimize processes, how to create more with less. And that understanding is power, is capability, is what allows us to build, to create, to improve. And the more people understand, the more people see fire the way you now see it, the more we can do. The more we can achieve, the more we can create. Because understanding is contagious, is multiplicative, is transformative. And you now have that understanding, and you can share, can teach, can spread, and make others see what you see. And when they do, when they understand, they're also transformed, and the cycle continues. And knowledge spreads, and understanding grows, and civilization advances. And all because you understand fire, because you see what it really is, because you don't accept mystery, you seek truth, and find it, and share it, and transform. And that's a gift, the greatest gift of all, gift of understanding, gift of science, gift of Feynman, and now it's yours, and you can pass it forward forever. And that's beautiful, that's profound, that's extraordinary. And that's why understanding fire matters, not just because it explains flame, but because it explains everything: energy, transformation, entropy, life, and death, and everything between. And once you understand, you see the world differently. And living in that world with that understanding is a gift, is a privilege, is extraordinary, and it's yours, now, forever.